All right, so for the homework, I graded 2 problems. I graded 5.4 question 2 and 5.7 question 8. And by and large, most people who did the correct problem got the correct answer, although a lot of people did the wrong problem for some reason. But I think it's the fault of the book, because when I started making my grading key, I was doing the wrong problem also. So if you did the wrong problem, but you did it correctly, then I gave you credit. But let's look at 5.4, question 2. So this was trying to find the greatest common divisor of pairs of integers. So the first part looked for the GCD of 615 and 120. And you always want to write the larger number as some expression involving the smaller number. Don't try to do 120 equals 1/6 times 615. You want to stick to integers. So if it asks for the GCD of 120 and 615, put them in this way. That's not really necessary. I'll show you why in a minute. But GCD of 615 and 120, so we write 615 equals, and how many times does 120 go into 615? It'll actually fit 5 times. And 5 times 120 is 600, so we've got an extra 15 left over. And now we're working with these two numbers. Okay, the 5 is irrelevant. This number here doesn't come into the calculation. The only thing that's relevant was the 120 and the remainder. So now we take those two numbers and we find their GCD. 120 equals 8 times 15 plus 0. So the 15 and the remainder are the relevant parts. Since the remainder is 0, we're done with Euclid's algorithm, and the previous remainder, that's the GCD. And it's the same process, whatever your numbers are. Don't try this with negative numbers. If one or both of your numbers are negative, convert them to positives and work with that, because it gets confusing otherwise. So let's look at GCD of 936 and 412. So write the larger one as something times the smaller one. So 412 will go in twice, plus some remainder. Well, the remainder here is 112. So we care about the smaller number and the remainder, so 412. And 112 will go in 3 times with a remainder of 76. So take the smaller number and the remainder. 112 equals 1 times 76 plus 36. And just keep going till you get down to 0. So 76 equals 2 times 36 is 72 plus 4. 36 equals 9 times 4 plus 0. Once you get down to a 0, the previous remainder is your GCD. All right, and then one more. GCD of 3672 and 1122. So exactly the same process. 3672 equals 3 times 1122. So obviously I used a calculator to do these. So 1122 equals 3 times 306, that's 918, with an extra 204. So use a 306 and 204. 306 equals 1 times 204 plus 102. And then 204 equals 2 times 102 plus 0. And so the previous remainder is the GCD. And if you do this in different ways, but you follow the procedure, you'll still get the same answer. For example, suppose we said, let's find the GCD of 120, 615. And we didn't know that we could switch the order of those. You can still use the same algorithm. because 120 would be 0 times 615 plus 120, right? 615 goes into 120 0 times, and your remainder is 120. And now you take these two, and you'll say 615 equals 5 times 120 plus 15, and we're doing the same thing we were doing before. We're going to get the same answer. Mm-hmm.
So you said the negatives turn into a positive. You mean just like pull a negative one out?
Yeah, because the GCD of, say, -8 and -12, or -8 and +12, if we want a positive factor, right, we usually only work with positives anyway when we're talking about greatest common divisors, but if for some reason you need to find the GCD of numbers that are negative, just work with the positive value, work with their absolute value. Because technically, -2 is a factor of 8, right? But it's -2 times -4. I don't know if we really want to count that. But if we're trying to reduce a fraction, -8 over -12, right, we find a common factor of 4 and divide that out. So just work with the absolute values. And even if you mess up, let's say that we think 120 only goes in 4 times. So it's 4 times 120 plus 135. I don't know if this works or not. I've never tried this. Maybe it doesn't work. It doesn't work. All right. But that's weird. Yeah, it should work. Okay, so let's take those. So 120 equals 0 times 135 plus 120. And then 135 equals 1 times 120 plus 15. And then 120 equals 8 times 15 plus 0. And there's your GCD. So even if you don't subtract off as many of these remainders as you should, you're still going to get the right answer. The reason this whole algorithm works is because when you take your original number and subtract a multiple of the second number, that second number and the remainder share the same common factors as your original first two numbers. So we could do a slow version of the Euclidean algorithm and just keep subtracting the second number and taking the remainder and keep iterating on this, and it would take more steps, but it would get us there. And what you didn't have with these exercises was an example where you come down to a 1, where your numbers are relatively prime. And let me just show you what that looks like. So GCD of, say, 13 and 3. So 13 equals 4 times 3. Let's do 13 and 5. Because this is a little more confusing. So 13 equals 2 times 5 plus 3. Take the second number and the remainder. 5 equals 1 times 3 plus 2. Take the 3 and the 2. 3 equals 1 times 2 plus 1. Take the 2 and the 1. 2 equals 2 times 1 plus 0. You still want to get down to where you're adding, where you've got a remainder of 0, and then the previous remainder is your GCD. And for some reason, if it comes down like this, sometimes people get to the 1, and then they say the 2 is the GCD. Right, and that's not the case. So go down until your remainder is 0, and then the previous remainder you had is the GCD. And your other edge case might be something like GCD of 50, 5. So 50 equals 10 times 5 plus 0. First line that we write, we've got a remainder of 0. Okay, that tells you that one of these divides the other. In particular, the smaller one divides the larger. So the smaller number is the GCD. And if you're coding this, you need to think about those edge cases. If you're not coding it, you probably realize as soon as you write this that 5 is a factor of both. But they need to be dealt with in code. Could be a recursive thing, yeah. And they'll probably have you start with something that uses GCD in 223. It's a good Java warm-up exercise. So you'll get to revisit this. All right, and then the other question I looked at was 5.7, number 8. And this asked you to find 5 to the 23rd modulo 11 using modular exponentiation. So 23 is 16 plus 4 plus 2 plus 1. So we need these powers of 5, mod 11, and then we can multiply them. So 5 to the first is just 5. 5 squared is 25. What's 25 mod 11? A lot of people got that wrong. I got some 4s, I got some 2s. So 22 is a factor of 11, a multiple of 11, so 25 minus 22 gets you to 3. So 5 to the 4th is just 5 to the squared, so 3 squared, which is 9. 5 to the 8th is 9 squared, which is 81. And 77 is the highest multiple of 11, so 77 to 81, that's a difference of 4. And if you like, you could have also said 9 is congruent to negative 2, and then 5 to the 8th would be negative 2 squared, which is also 4. So that'll get you there a little easier. And then 5 to the 16th is 4 squared, which is 16, which is 5. And if you had to do higher powers at this point, it takes no effort. Well, it takes a little effort because you have to write all of this. But since 5 to the 16th is 5, we already know 5 squared is 3, 3 squared is 9, 9 squared is 4, 4 squared is 5. We've got a pattern. So if you had to do this for, 20 powers of 5, you can just keep repeating this pattern as soon as one of these matches something that you've already got. But we didn't have to do that for this problem. We only needed these first 5. And so 5 to the 23rd is 5 to the 16th times 5 to the 4th times 5 squared times 5 to the 1st, which is 5 times 9 times 3 times 5. And you can multiply these out if you have a calculator, or you can do it in pieces. This is 45 times 3 times 5. 45 is congruent to 1. It's 1 more than 44. So this is 1 times 3 times 5, which is 15, which is 4 more than 11. So your final answer is 4. So if you get a GCD problem on a test, or you get a modular exponentiation problem on a test, make sure you show your work. Okay, sometimes you want to do a little scratch work on the side to figure out what the answer is and then write down the answer. I've got to see that scratch work. Okay, I want to see the process for a few reasons. One, to make sure that you're doing it correctly, but two, if you get the wrong answer, but the reason is that, for some reason you thought that 25 was congruent to 4, right? If I can see that, I'm not worried about it. I might take off a point, right? But if I can't see that and I just see the wrong answer at the end, then you're going to lose 10 or 15 points, whatever the problem's worth. So make sure you always show your work, definitely on homeworks, also on exams. All right, so any questions on that or any of the other homeworks? I don't know if I'll get to it over the weekend. I guess I could try. But the exam's not till Friday, so. But yeah, I'll put something up. Basically, everything that we've talked about is fair game up through number theory. So next week, we're going to start talking about counting and permutations, and that will not be on the midterm. Absolutely. Hopeless without my beautiful scroll wheel. 5.2, number 6. This one? Okay. So we talked a little bit about this the other day without giving it away. So let's finish this. So here's a set of 5 integers. And we want to prove that this contains a multiple of 5. For any n. Where n's an integer, as usual. Doesn't even have to be positive, but for any positive integer n. So multiples, think about doing things modulo something, right? We're looking for a multiple of 5, so think about doing things modulo 5. So prove that for any n, let's say one of the following is true. At least one. So instead of saying that one of these is a multiple of 5, let's say either n is congruent to 0 mod 5, or n plus 4 is congruent to 0, or, and so on. Okay, I guess so. So one of these has to be true. That's the same thing as saying one of those is a multiple of 5. It's saying that one of those is congruent to 0 mod 5. And our trick when we're trying to make wide sweeping statements about numbers modulo something is to realize that every number is congruent to one of a small set of possible things. In modulo 5, either n is congruent to 0, 1, 2, 3, or 4, modulo 5. So we're trying to prove this statement for any n. Well, we know that for any n you pick, one of these 5 things is true. Right? Division algorithm tells us every number will be congruent to either 0, 1, 2, 3, or 5. So we can do a proof by cases. So case 0, suppose n is congruent to 0. Well, then we've proven that n is congruent to 0, right? And this theorem says that for at least one of these 5 statements will be true. So if n is congruent to 0, at least one of these 5 statements is true. Case 1, n is congruent to 1. Well, if n is congruent to 1, n plus 4 is congruent to 1 plus 4, which is 5, which is 0. So if n is congruent to 1, at least one of these statements is true. And you work through all 5 cases. Case 4, n is congruent to 4, and in that case, n plus 16 is congruent to 4 plus 16, which is congruent to 20, which is congruent to 0. And so this statement's true. So you can show that in any of the 5 possible cases, one of these statements is true. And since those are the only 5 possible cases, the statements are always true. Yeah?
So I kind of stuck with sets.
Okay.
I wrote out n mod 5, n minus 1 mod 5 a ton of times. Is it like okay to draw a set and then say this set mod 5? Is that
If you're careful, you should be able to. Was it a finite set or an infinite set?
a finite set containing n, n minus 1, no, n plus 4, n plus 8.
Okay.
I said mod 5. Is that, because I didn't do that. I said n plus 4 mod 5, n plus 8 mod 5.
Mm-hmm.
I got the pen.
So someone who's very rigid about this might argue that that's not necessarily valid, because 2 of those things might be congruent to each other, and then you'd be writing a set with multiple things. But that doesn't bother me for the feel of the proof.
And another, when you write in the 3 equal sign, that's like logical equivalence, right?
No, that's congruence here, right? So if we follow that with mod 5, we're talking about congruence. Logical equivalence needs a proposition on each side, right? This proposition is logically equivalent to that, and these are not propositions, right? Although this whole thing is technically a proposition, and this whole statement, at least one of the following is true for any n, that's a proposition. But yeah, it's the same symbol, unfortunately, as logical equivalence, but here we're talking about congruence. So left and right side have the same remainder when you divide by 5.
So I said, another question similar to the first one. So I said n mod, well, n plus 4 mod 5 equals, I brought up the word n minus 1 mod 5. Is that true?
You really got to say congruent.
Okay.
Because, yeah, so it's a little bit of a terminology thing. But 13 is congruent to 3 mod 5. They both have a remainder of 3 when you divide by 5. But that equality symbol, right, 13 is not the same number as 3 if we're talking about integers. But maybe if we had a different kind of equal symbol, an equal 5 symbol, which means equal modulo 5, then we could do that.
And if I said 13 mod 5 equals 3 mod 5, is that?
That should be okay, as long as we understand that when we say 13 mod 5, we're talking about that magic number between 0 and 4, right? But technically, 13 mod 5, so I won't do something like this on a test, but when I see this, to me, that means 3. Okay, it means the number between 0 and 4 that 13 is congruent to. But technically, 13 is also congruent to 23 mod 5. And so one might look at this and be thinking of that. So, but the safest thing is to stick to congruence. And then you're saying it may not be the same integer, but it has the same remainder when you divide by 5. And usually when you're working with things modulo something, you're using congruence for equality, you're doing addition, subtraction, and multiplication modulo 5. And you're really using these sort of special operators, this plus 5, this minus 5, and this times 5 operator, which means multiply the integers and then reduce modulo 5. But if we know what we're doing, we usually suppress all of that and just say 5 plus 3 is equal to 3, modulo 5, for example. Other questions? All right, well, let's start some cryptography. And I don't know if we'll make it all the way to RSA today, but that's okay. So basic idea of a crypto system. You have a message, which we generally call plain text. It's something written in a form that anybody who understands the language, for example, can easily read. So here's a message. It says plain text. We can all read what that says. Okay, so here's another message. So cookies at noon. You want to tell your friend you're going to have cookies available at noon. But you don't want everybody to know this. You just want your friend to know this. So you want to send this message to your friend, but the problem is there's really no secure communication channel. There may be today. Quantum may do it. But certainly back when you had to give the message to somebody and they had to carry it over to the person it was intended for, somebody can intercept them and steal that piece of paper, right? If they're riding a horse, they can block their path and pull them off the horse and take the piece of paper. So we've generally assumed that transmission lines are insecure. If I take this and I put it in an envelope and I stick it in my friend's mailbox, somebody can come along and open the mailbox, open the envelope, and find out I'm going to have cookies at noon. Okay? So the idea of encryption is let's take this plain text and run it through some kind of cipher and get out some crypted text, which says, 43 at XYYPL1 underscore $. And then this crypted text or cipher text is the thing that I put in an envelope and leave at my friend's door, or give to somebody to travel across the country and hand the message to my friend, right? So crypted text or cipher text. And if somebody intercepts the message on the way to the recipient, they look at the piece of paper and it says this, they have no idea what that message says. Okay, so that's a basic setup for a crypto system. It's a way to encode plain text so that if somebody else reads it, they don't know what the message is. But hopefully the person that you intend to read it has a way of taking this and translating it back into cookies at noon. So they can take their encrypted text and they can run it through some kind of decipher, and out comes plain text. And there's different ways that you can encrypt plain text. But another general assumption is that algorithms are never secret. Okay? If you have a way of doing this conversion, for example, we're going to take the ASCII codes of each character and we're going to reverse them. So something which was ASCII code that looked like this, we're going to reverse it and use whatever character this corresponds to. And so now these plain letters are going to end up being weird characters and escape sequences and stuff like that. So certainly if you just look at the crypted message, you're not going to know what it is. But as soon as you figure out that this is the encryption algorithm, all bets are off. You can take the encrypted message and you can decrypt it just as easily as the recipient. So we use passwords. So this cipher algorithm is some complex algorithm that jumbles up the information, but it also requires a password. So here's a very old algorithm. This is called a Caesar cipher. So your password is an integer from 1 to 25. So let's say the password is 3. So what the Caesar cipher does is it takes each character and it adds 3 to it. So C becomes an F, O becomes an R, O becomes an R, K becomes an N, I becomes an L, E becomes an H, and S becomes a V. Is it a T? No, it's a V. Yeah. So now this is the ciphertext that you send. And if somebody intercepts it, they can't decrypt it. They know what the algorithm is that you're using, but if they don't know the password, they can't reverse this process. But your friend who also knows the password uses an algorithm to reverse this. So they take each of these. So here we were adding 3 to each letter. They take each of these and they subtract 3. And they get back the original message. All right, so that's, Caesar apparently actually used this, right, thousands of years ago. That's the basic idea of encryption, decryption. You have a password and you have an algorithm. You put the password into the algorithm, you turn the crank, and out pops gibberish. And unless you know what the password is, you can't reverse it. But if you know the password, you can turn the crank in the reverse direction and turn the gibberish back into plain text. So a Caesar cipher is a particular case of something called a shift cipher. And a shift cipher basically just bumps up or down each piece of information by some fixed amount. And it's incredibly insecure, right, for a variety of reasons. Well, one, you could simply try all 26 possible passwords, right, until you get something that looks readable. So anybody here ever have a spy decoder ring from a box of cereal? They don't do that much anymore, but I had one. It was cool. It was basically just a circle with all the letters around it, and then a bigger circle with letters around it, but you could turn the outer circle, and depending on where you turn it, if you moved it 3 spots over, then A and D would line up, and B and E would line up, and so you could take your message and use your decoder ring to encrypt a message or to decode it. It was pretty fun. But there's only 26 possible passwords, right? And one of them doesn't do any encryption at all. And so you could just try all of them. So that's not very secure. And you can do fancier things. But an easy way to attack this is a frequency analysis. So if you know that the message being encrypted is written in English, and you know what English looks like, you can look at large amounts of random text written in English and see how often each letter appears. And the letter E is the most common letter, right? It's the one you buy. If you want to buy a vowel on Wheel of Fortune, buy an E. And a Z is very infrequent, right? So if you look at your most frequent letters, and now you take a piece of crypted text, and you find which letters in that crypted text are most common, there's a good chance the most common letter in that crypted text corresponds to E. So if the most common letter is G, how do you get from an E to a G? You add 3, you would guess your password's 3. And now you subtract 3 from your text and you see if it's readable. And there's all kinds of frequency analysis you can use to attack these things. So shift ciphers aren't very secure. And you can try to get fancier. You can add some function of your character position modulated by a password. And there's different things you can do. But in general, we're pretty good at cracking these things. So another kind of cipher is a transposition cipher. And this is built around the idea of a permutation. So we have some function from Z to Z. And I'm going to use this funny notation Z3 to mean the integers up to but not including 3. So the integers 0, 1, and 2. So Z3 means 0, 1, 2. So I've got this function sigma from that set of integers to itself. And suppose sigma looks like this. So it takes 0 to 2, it takes 1 to 1, and it takes 2 to 0. And you want this to be a bijective map. So here's what we do. To encrypt a message, we break it into groups of 3. So we'll pad some spaces at the end. And we rearrange the letters. So our first character, the C, is going to become character position 2. That's actually our third character. Character 1 is going to stay where it is, and character 2 is going to go to the beginning. So that's going to go like that, and that, and that. So we've got OOC. And now K is going to become our third character. I is going to stay where it is. E is going to go in the middle. And then S is going to come down to the end. Our space will stay there, and our space will stay there. So our message cookies becomes useek space space S. You can't do a frequency analysis on that. But we can do an analysis on things like the letter T followed by the letter H. We know that occurs pretty frequently. And sometimes, you know, if these blocks are bigger than 3, there's a good chance there's going to be a lot of THs in the middle of a block. And if we find repeated occurrences of T and H, and we know that they're this far apart, right, we can start to guess how those were. We know that they were adjacent to begin with, and we can start to build up over enough data some ideas about what this permutation looks like. So transposition ciphers are pretty easy to crack. Now to reverse this, right, if we know this function sigma, we can define the inverse. So the inverse of 2 is 0, the inverse of 1 is 1, and the inverse of 0 is 2. And so character 2 goes to the beginning, 0 stays where it is. This becomes COO, character 2 goes to the beginning, 1 stays in the middle, and 0 goes to the end. And there's your original message. Okay, all of these have one thing in common. This password for deciphering and this password for ciphering are the same. Or at least one is derivable from the other. For a Caesar cipher, if you encipher with 3, you decipher with -3. With a transposition, if you cipher with sigma, you decipher with the inverse of sigma. Okay, so these are called symmetric key ciphers. Symmetric because the way that you encrypt and the way that you decrypt use the same information, the same secret piece of information. And there's a few problems with this. One, if I'm going to send messages to a friend across the country, I've got to somehow tell them what the password is that I'm using. And how do I send them that password securely? I could put it in an envelope and mail it to them, but what if somebody opens the envelope and they see the password? So a friend and I, before we parted ways geographically, we set up a secret password, right, so we could do this. But if you don't do that ahead of time, you have this problem of how do you convey a password securely? The second problem is, suppose I want to send a message to 20 different people, and I want to do it securely. I have to give each of them a password. And I've got to keep track of what's my password for you, what's my password for you, and so on. So what's a situation where we try to send information to somebody, where millions of us are trying to send information to the same somebody, and we would each need the same password? Is there anything we do in our daily life that might cause that situation to occur? Say again? Banking, right? You go to Amazon, you want to buy something, you type in your credit card number. That's not going over in plain text, right? Anybody can pick up what's coming out of your Wi-Fi connection on its way to wherever. So it's got to be encrypted. But did you talk to Amazon and say, hey, what's the password I should use to send you this information? No. And the only way you could do that is if they sent you a password somehow, and how do you know that that password wasn't intercepted by somebody? So the reason that online commerce works is because we can encipher with password 1, but you need password 2 to decipher. And password 1 is the same for everybody. This is public. Amazon makes this available to any browser that wants to send information. They find out what the password is they need to encrypt the information. But password 2, which is used to decrypt the information, that's private. Nobody knows that except Amazon. And this means that everybody can encrypt their message and send it to Amazon. And it doesn't matter if somebody sees that encrypted message, they have no way to decode it unless they know this private password. Okay, this is why e-commerce works. This is why the internet is usable today. Because we have this so-called asymmetric key system. It's also sometimes called a public-private key system. And this was developed in the 70s by some grad students and a researcher, and there's an interesting story. I'll tell you a little bit more about it on Tuesday. The history of this is pretty interesting, and it involved a fair amount of, well, good part of genius, right? Good part guts, because there were threats being made against these researchers involving things like long prison sentences for publishing their research related to this. And it was very controversial when this was being developed, because this was a way that people could share information secretly, and even the government couldn't find out what you were saying. And that made some people nervous. So we're out of time today. We don't have class Monday, but Tuesday we'll talk a little about the background of this, and then we'll actually see how RSA works. RSA is one of these asymmetric key ciphers. So we'll do that, and that'll finish up our number theory unit. All right, so have a good weekend, and I will see you next time. Monday's President's Day, no class.